So this video is going to be a quick review of how we use these rules for series and parallel and in calculating the charge or the potential on an element that's embedded in a network. So these are our rules. This is how we add series. They add as inverse. And this is how we add parallel. They just add straight out. If we have two or more elements that are in parallel, the potential across each element is the same. And if they're in parallel, the charges add. I'm going to give you an example in a moment. If we are in series, the charge is the same across each element, and the potential adds. So we would add up the potential across each element to get the potential on that branch. And then this is the equation that we use that relates capacitance in farads, charge in coulombs, to potential, which is in volts. And we can use this equation as many times as we want, writing the same subscripts on it each time. All right, so I have a short example here. Let's suppose we had this network, and at the end of the problem we could be told that these terminals are hooked up to a battery with a known potential difference. But let's say I have A and B oriented or arranged this way, and C here. So my first step, if I was calculating the equivalent capacitance of this, would be to combine A and B in parallel, and I would use the parallel combination rules to calculate that. And I recommend resketching, as you've seen me do, resketch. So, and what we're resketching here is if we were to remove A and B and replace it with a capacitor that had the same capacitance as if you had A and B connected in parallel. So that's my reduced AB capacitor plus C. Those are in series. Now let's look at what the rules are. If I'm looking at this picture, A and B being in series with C, the rules from the previous side of my board says the charge is the same. So the charge on the whole thing, the equivalent, or we could also say on this branch, is going to be the charge on C, is going to be the charge on AB. One way to remember this might be that if you think about current flowing through a branch, the same charge has to go across this one as across this one. It's like a river. If you have 2 points on a river and there are no branches, no other ways for the water to go, if a certain amount of water goes across this spot, the same amount of water has to go across another spot. So the charge is the same on AB, so QAB is QC. And the potential adds. So basically across this, the potential across the whole thing gets divvied up between these two elements. Now, when we go back a step and look at this picture, and we're gonna focus now on just A and B, because we would have taken care of C over here. We would have calculated charge on C and potential on C using that information. So we're gonna look just at A and B. The potential across this whole branch right here is going to be the same as the potential across A and the potential across B. So the volts going here are the same as there. And because they're in parallel, the charges add. So you could think of this as the water gets split. We've got a fork in the river. Some of it goes this way, some of it goes that way, and it's all gonna meet back up over here. So since some of it goes each way, I'm going to have the charge on A plus the charge on B has to equal the charge on the whole thing, because it gets split because they're in parallel. But when they meet back over here, it's the same amount because we have the charge on AB and C being equivalent.